All right, so let's look at an example. All right, now let's make it a little spicy, a little fun. We'll have 1 minus I times z minus 2. All right, so first things first, let's get this in our form where we can see the magnification, we can see the translation, we can see the rotation, see all the parts. First thing we need to do is compute the modulus of the complex number that's multiplying z, and that's easy enough to do because that's just root 2. So that means that our function, then, we can pull it apart as root 2, 1 minus I over root 2, z, plus negative 2. All right, and there we go. We've got our magnification, we got our rotation, and we got our translation. Look at excellent handwriting today. Been real good, I know. All right, so equipped with all of this, then give me any shape, I can draw it and tell you exactly how this function works. However, we want to be a little careful. Obviously, this complex number is rotating, but right, at first glance, 1 minus I over root 2, you might not immediately recognize what that rotation will be. So what do we need to figure out? Well, you just need to figure out your principal argument of 1 minus I all over root 2. Now let's remind ourselves of where this thing is living. Real part 1, negative I here. Okay. So that's 1 minus I, and then we scale it by a factor of root 2. So that would give me my 1 minus I over root 2. Now note something, 1 over I minus root 2 has to be on the unit circle, so we know it's there. And if we're following that line right there, we can see, oh, hey, that's a rotation clockwise by pi over 4, right? And so note the principal argument, of course, we take that to be negative pi over 4 in this case. Again, if you're in the top half plane, the principal argument is the usual 0 to pi, but on the bottom half, we go negative pi to 0 rather than pi to 2 pi. And again, that's done for reasons. So equipped with this now, I have all the ingredients I need to tell you exactly what happens to this triangle, 0, 1, I, when I feed it into my function f. And the exact details of all of this I don't need to be too worried about because, again, I know what the rotation factor is. It's going to rotate it clockwise by pi over 4. I know it magnifies it by root 2, and then I know it shifts it by negative 2 in the real numbers. So visually, I can go through it. We start with my triangle. And again, remember, you do it in the following order. It rotates, and we know it's going to rotate it pi over 4 in that direction, so it looks like that. We know it magnifies it by a factor of root 2, so just going to make it a little bit bigger. And it's going to translate, and now here we need to be careful with the translation. Negative 2, so it's shifting it to the left by 2 units. So if I add a real number, it shifts to the right. If I subtract a positive real number, it goes to the left. If I add a complex number, it's going to go up, and if I subtract complex numbers, it goes down. So the translation is going to go to negative 2, and now here's where we got to be a little careful about the details. After I do translate it, is it going to cross the axis? It's not going to, but now's a good time to follow each one of the points and see exactly where they go. So for example, 0, we know rotating it keeps it 0. Magnifying it keeps it 0, and then subtracting negative 2 moves it over there. Okay. Now 1 is going to be a little interesting. So 1, we know, is going to rotate. So 1 is going to go to 1 minus I all over root 2. It will then magnify by a factor of root 2. So we'll go to 1 minus I, like that, which will be down there. And then it is going to get subtracted by negative 2, giving me a negative 1, negative I. So this point right here is negative 1, negative I, And this point we can also trace out that will be 1 negative 1 plus I. So there we go. It gives a more accurate drawing of the picture. So if you want all the details, that's how you can do that. All right, beautiful. All right, and there we go. And now you can do this for any complex linear, AZ plus B, and you can not only do that for every AZ plus B, you can also now pretty easily see what it does to every shape. So now note, AZ plus B is going to rotate, magnify, and translate things. So shapes such as triangles are going to go to triangles, circles are going to go to circles, so on and so forth. Shapes are not going to get screwed up. Let's look at another function that's going to guarantee that shapes get a little goofed up. So the next function analytic that we're going to look at that's a little bit more spicy one over z. Ooh. So note 1 over z analytic, but of course it's got a simple pole at 0, but it's still analytic everywhere else. This particular function is also, just like AZ plus B, actually two complex functions in disguise. Because if I put z into its polar form, and again note z is never equal to 0, so this is always a valid thing to look at. 1 over z turns into that, and note that there is effectively two things going on here. The r turns into a 1 over r, and the theta turns into a negative theta. Ah, interesting. All right, so it turns out that there's, just like AZ plus B, two things going on, so let's break these two down and talk about visually what they're doing. So, the first thing, changing the r to 1 over r, this is called an inversion of the unit circle. So, specifically, if our function just is 1 over r e to the I theta, so depending on your r, we can see where you go on the unit circle based on this function. All right, so if we look at our unit circle, there we go. So if r is equal to 1, that means you're on the unit circle, and our formula says 1 over r. Well, r is 1, so 1 over r is nothing, so if your r is equal to 1, you don't do nothing. Now let's say your r is bigger than 1, so let's say you've got a point hanging out over here, r is bigger than 1. Well, then you get reduced by a factor of 1 over r. So note if that's true, 1 over r is less than 1 in modulus. So this function will actually keep you on the same angle, but it's going to pull you inside of the circle in the same direction. And if r is less than 1, then 1 over r is bigger than 1. So if you're inside the circle, let's say down over here, all right, well, 1 over r is bigger than r, so you're in the same direction, but now you've been pushed outside of the circle. So hence the name inversion of the unit circle. Everything outside the unit circle gets pushed into the unit circle, everything inside the unit circle gets pushed out, and everything on the boundary just chills. Cool. All right, so the first component of 1 over z, the 1 over r, that's how it's going to treat our points. If you're on the circle, nothing happens. If you're outside the circle, you go in, and if you're inside the circle, you go out. All right. Now, what about the other part of the expression, which was the negative I theta? Well, if you really look at that, you see that it's simply conjugation. And as we've already discussed, we know what conjugation is, so there's z. So So note, if this is theta, then that's clearly negative theta that's going on there. This is simply a reflection. Across the x-axis, or the real axis. So if we want to look at the behavior of 1 over z, it's pretty easy to see what it's going to do. You just take your points and then see if it's on the unit circle, put it through, so the order in which you do it is you take your points and it doesn't matter the order in which you do it. You can do the inversion part and then reflect it across the axis, or you reflect it across the axis and do the inversion part. So with that geometric intuition of what 1 over z is going to do, let's prove something really cool. All right, so we're going to look at the following: what happens to the following set under reciprocals. So note, this right here is the set of complex numbers with real part equaling 1. So my question is, what happens when I take a line in the complex plane and look at 1 over z? Fascinating, correct? All right, well, geometrically, I can kind of get a pretty good idea of what's going on, because again, what you want to compare this to is the unit circle. So look at the unit circle. All right. Now, obviously, 1 is going to stay. Everything else on the line, note, will have a radius bigger than 1. It's outside of the unit circle. So we know by how 1 over z is supposed to work, it's going to take this and bring it into the unit circle. We also know that that will happen first. And since it's 1 over z, we also know that there will be a reflection down there. And likewise, if I take a point over here, it will come into the circle and then it will reflect. And you can see every point is going to behave that way, so everything above is going to get inverted into the unit circle and then get reflected into the bottom part. So all of that is going to kind of go down. So the question, though, is, right, what shape am I going to get? Okay. So we can obviously do this sort of like, all right, well, I know it's going to invert it through the unit circle, so we know everything's going to get pushed inside of the unit circle and then reflected across the axis. Likewise here. But what shape is this going to form? And if you're following the R here, it's here, and then it's here, and then it goes down. And then if you kind of think, it's going to take this top part of the line, and it really seems like it's going to put it in and bend it, right? Likewise here, this is going to start there, and then this is going to start filling out this curve, and it's going to have to start bending it, because it's reflecting, right, it's pushing it into the circle and then flipping it out, and, oh, hey, kind of looks like it's going to make a circle or some shit. I don't know. So to really isolate what the shape is going to look like, which I'm cheating and telling you it's going to be, a circle. In order to really kind of see that and get a feel for it, we are going to have to do the following. So let's break it down. All right. So if your real part is 1, that means you look like 1 plus IB. All right, plug in 1 plus IB into my function. Remember, the trick is to multiply by the conjugate. And if you do that here, this cleans up as follows. So you'll have a 1 plus 1b squared and a I negative b over 1 plus b squared. Okay. All right, so we did stuff like this a while ago. And now note something here. We can look at some key values of b. Obviously, when I plug in b equals 1, not 1, b equals 0, that's corresponding to the real number 1, right? We already know what this is going to be. This is going to be 1. We know that the point 1 stays put. It's on the unit circle. Now let's look at two other key factors of b. If b is equal to 1, and I plug that into my formula right here, I'll get f of 1 plus ib is going to be 1/2 minus 1/2 I. Likewise, if b is negative 1, I'm going to get 1 plus ib, 1/2 plus 1/2 I. So with those key values in mind and the geometry that we've drawn out, we know that once you get up here to an r value of 1, we're going to go down to here, which I've now just deduced is 1/2 minus 1/2 I. And for negative 1, right over here, we know it's going to go to that part right there, which I know is 1/2 plus 1/2 I. Seems like, I don't know, maybe that's the bottom of the circle and that's the top of the circle, so the center of my circle should be happening at 1/2, and that is going to be kind of the trick here now. Because now, note, if I were to look at f of z minus 1/2, so note that would be 1 plus 1 over b squared plus I negative b 1 over b squared minus 1/2. I can clean this up and it turns into 1 minus b squared all over 2, 1 plus b squared in the real part, and in the imaginary part of negative b, 1 plus b squared, like that. So furthermore, if I were to take the modulus of this piece, and the gory details are in the type notes, so you can check it out. But if you were to take the modulus of this, note it would start with, I'll give you the starting point. All this junk squared and all of that junk squared. It turns out that if you work out all the details, inside you'll get 1 over root 4. It may not immediately look like it, but it's true. That is not... Oh my god, I'm trying to pick the erase. I'm trying to make that cleared up. So in the type notes, the actual explicit details of how this turns into 1/2 is there, and you can work out the details. And so now note, we have proven that f of z minus 1/2 always has modulus 1/2. Like I said, the actual details of that, you can check it out. So if I go back visually, we started with real part is equal to 1. We're looking at the function f of z is equal to 1 over z. And when I feed the real part equaling 1 into it, note 1 stays the same. We know that 1 plus I is going to go to 1/2. Right, note that's this part of it right here. 1 minus I is going to go to 1/2 plus 1/2 I. Oh my god. Okay, 1/2. This part down here is going to go like that, and we know that over here we'll have the 1/2 minus 1/2 I. Right, so we've got a circle centered at 1/2 with radius 1/2, but with a big little problem right there. So the image of the real part of z equaling 1 under is the circle missing precisely 1 point, which is w equals 0. So this part of the line here becomes this top half of the circle. This part of the line up here becomes this bottom half of the circle. And let's wrap up today with the final point of order. You can include the w equals 0 part of the circle, that's the point that's missing, by going, well, this line goes off forever in both directions. What if it looped around and met at a certain point? So this is a technique that we're going to exploit when we combine linear and 1 over z, linear fractional. Oh, look at that. That's the title of 3.3. So what you do is you add infinity to c. This creates what is called the extended complex numbers. And you define 1 over infinity to be what you want it to be, which is 0. And likewise, you define 1 over 0 to be what you want it to be, which is infinity. So with the extended complex numbers, so an extended complex line, so a line in the complex plane plus infinity, will map to a circle under 1 over z, because it's going to send infinity to the missing point 0. Pretty neat. And in fact, you could verify there's nothing special about the real part equaling 1. You can do this for real part equaling 4 billion, and you can do it for real part equaling -6. And you can even do it for the imaginary parts if you really want to sink your teeth into some fun there. Other lines, so non-vertical and non-horizontal lines, the story's a little more complicated, but you can still basically do the exact same analysis we just did. But yeah, neat stuff. All right, so we've seen what linear mappings do in the complex plane. We've seen what reciprocating does. Our goal, and this is what we'll do in class on Tuesday, is to combine the two, so linear and fractional, which is the title of 3.3. So we'll investigate those, and with that in hand, we'll then go after conformal mappings, and I think we'll just call it a class after that. All right, that's it for today. Thank you.